Welcome back to Think Thrice. Today we're going to investigate the Cauchy-Euler equation, a fun differential equation. If you're not familiar with the Cauchy-Euler equation, it's an equation of this form where we have the second degree term in front of the second order y derivative, first degree term in front of the first order, and then a 0th degree in front of the 0th order. And we can have any constant coefficients as long as they are non-zero. Okay? So generally, we're going to show you in a second how I would solve this, but we can show that for this particular Cauchy-Euler equation, one of the solutions is y equals c1 over x. And as we learn in our class, we can jump immediately and say that therefore y2 equals c2 over x times ln of x is also a solution. So we kind of magically pull this out where we're adding this ln of x to our existing solution. So today we're going to talk about where that ln of x actually comes from and how we get to it. Okay, so to start off, I'm going to look at our equation up here and talk about how we can solve it. So let's assume that we have an answer of the form y equals x to the m. So if we do that, our first derivative is going to be m times x to the m minus 1, and our second derivative is m times m minus 1 times x to the m minus 2. So if I plug those into my original equation, I'm going to get x squared times my second derivative, which is m times m minus 1 x to the m minus 2 plus 3x times my first derivative, which is m times x to the m minus 1 plus y, which is my x to the m term. And this whole thing is equal to 0. So if you notice here, I have this x squared exponent and this x minus to the m minus 2. And if I take x to the m minus 2 and multiply it by x squared, that's just going to be x to the m. I see the same thing here with my x term and my x to the m minus 1. So what this tells me is I can just rewrite this as x to the m times m minus 1 plus 3m plus 1 is equal to 0. Or more simply, this is going to be m squared minus m plus 3m, so plus 2m plus 1 is equal to 0. And I can rewrite that as x to the m times m plus 1 squared is equal to 0. So notice I have a repeated root here, m plus 1, but this tells me that in order for this statement on the left to be true for all x, I need m is equal to negative 1. So what does that tell me? That tells me that one of my solutions is going to be x to the x to the negative 1. And it turns out I can multiply that by any constant, and I'm fine. So I can rewrite that as c1 over x. So that's going to be one of my solutions. And then if you take a differential equations class, they might tell you to pop out your second solution, and your second solution is just going to be y2 equals your first solution times ln of x. And we kind of magically pull out this ln of x. I don't like magic, so let's go ahead and figure out where that comes from. So the method we're going to use to figure out where that comes from is called reduction of order. Okay, so let's look at a general Cauchy-Euler and move forward from there. So in general terms, every Cauchy-Euler equation that's second order can be written like ax squared times the second derivative of y plus bx times the first derivative of y plus c is equal to 0. Okay? Cy is equal to 0. Okay, so that's our general Cauchy-Euler expression. So in order to solve for my term, if I use the same method as above, I'm going to get the expression a times m minus 1 plus b times m plus c is equal to 0, which I can simplify to, or I can distribute to am squared plus b minus a times m plus c is equal to 0. Okay, so if I want to get my general solution here, I can take this guy, use the quadratic equation, and I get m equals negative this middle term, so I'm going to get a minus b plus or minus the square root of the middle term squared, b minus a squared minus 4ac over 2a. And remember, we're dealing with the case where we have repeated roots. So if we have repeated roots like we do here, that means that this radical is going to be 0. So we're going to be left with our m terms that are just equal to a minus b over 2a. Okay, so this restricts our solution set significantly. All right, so what reduction of order does, reduction of order says that we can reduce this to a first order equation if we make an assumption. So since we know that y equals x to the m is a solution, let's assume that y2 equal to u x to the m is also a solution. So we have a product of u, some new function, and x to the m. And our goal is to figure out what that u function is. So when we go into our equation here, we're going to assume y2 equals u x to the m. So we can do a few things. So we can see the derivative of y2 is going to be u prime x to the m plus u m x to the m minus 1. And our second derivative is going to be u second derivative x to the m plus 2 u prime m x to the m minus 1 plus u m minus 1 x to the m minus 2. All right, so here's where it gets a little bit interesting with our problem here. So we're going to go ahead and plug these into our general Cauchy-Euler equation. So we're going to get a times x squared times our second derivative, which is u double prime x to the m plus 2u prime m x to the m minus 1 plus u m minus 1 x to the m minus 2 plus bx times u prime x to the m plus u m x to the m minus 1 plus c u x to the m. That whole thing is going to be equal to 0. I can then multiply those out, and I'm going to get u second derivative times a x to the m plus 2 plus 2a u prime m x to the m plus 1 plus u m a m minus 1 x to the m plus b u prime x to the m plus 1 plus u m b x to the m plus c u x to the m is equal to 0. So I'm going to go ahead and pull a few things out. So I'm going to pull out this term, and this term. And if we pull those out, we can see that we have x to the m in all three of those. And we're going to be left with u in all three of those as well, times m minus 1 plus times a plus b m plus c. And if you look at this, we've already shown above that this is equal to 0. So those three terms are all going to be 0 in our expression. And we are now left with u double prime ax to the m plus 2 plus, and then if we look at both of these expressions, I have x to the m plus 1 in both expressions, and I have u prime. So u prime x to the m plus 1 times 2a m plus b equal to 0. All right, so we're getting somewhere now. So I see that 2am plus b there, and I see these other terms. So what we're going to do now is we're going to go back and we're going to say, hey, we already figured out what m was. M is a minus b over 2a. And we're going to put that into our equation. So if we plug that in, we're going to get u double prime a x to the a minus b over 2a plus 2 plus u prime x to the a minus b over 2a plus 1 times 2a times a minus b over 2a plus b is equal to 0. And some great things happen here. So first, we see that these two a's are going to cancel, and I'm left with a minus b plus b. A minus b plus b, those b's cancel, and I'm left with just that a in that expression. Over here, I have this 2 term and this 1 term. I'm going to transform that 2 into 4a over 2a, and I'm going to transform that 1 into 2a over 2a. So what I'm going to be left with here is the second derivative of u times a times x to the 5a minus b over 2a plus u prime times x to the 3a minus b over 2a times a is equal to 0. I started my problem by saying that a was non-zero, so this guy and this guy can be divided out. And now I have something that I can go ahead and separate variables. So let's do a quick substitution. What we notice here is we have a second derivative term and a first derivative term, and no zeroth derivative. Okay, so I don't have any just u in there. So we're going to do a quick substitution and say, what if we make u prime equal to v? That leaves us with v prime x to the 5a minus b over 2a plus v x to the 3a minus b over 2a is equal to 0. And we can use separation of variables to solve this guy. So let's go ahead and do that. We're going to get v prime x to the 5a minus b over 2a is equal to negative v x to the 3a minus b over 2a. I can divide the v's onto the left side, the x terms onto the right, and I'm going to get v prime over v is equal to negative x to the 3a minus b over 2a minus 5a minus b over 2a. All right, and if we look at this, this is going to simplify considerably. So I have this negative b minus negative b, so those two guys are going to cancel. And 3a over 2a minus 5a over 2a is going to be 3 halves minus 5 halves, which is just x to the negative 1. And there's a negative sign there. All right, so we're looking pretty good at this point. So let's go ahead and work through the solution. So dv over v is going to be equal to negative 1 over x dx. I can integrate both sides, and I'm going to be left with ln of v is equal to negative ln of x plus some constant. I'll call that constant c1 for now. At this point, if I raise both of these guys to an exponent, I'm going to be left with v is equal to, I can put that negative, move it inside, make this x to the negative 1. This is going to be 1 over x times some that constant there, c1. Okay? But we remember is that v is equal to u prime. So what this is going to be is u prime, and I can go ahead one step further and say du equals c1 dx over x. I can integrate both of these sides, and I get that my u is equal to c1 ln of x plus some constant, which I'll call c2. All right, so I said that this was some term that, remember why we did this? We did this because we assumed we had a solution where y equal to u x to the m is also a solution. So what this means is that my second solution, y2, is going to be u times x to the m, which means I have c1 ln of x times x to the m plus c2 x to the m. And now I have a linear combination, or a combination of my two answers here. So I have my term which I was looking for, as well as my original term. So hopefully that was interesting, how we went ahead and derived that second answer. It's pretty straightforward. It's a little bit circuitous as we go through the path, but we're able to get there. Thank you for joining me again at Think Thrice, and hope to see you next time. If you enjoyed the video, go ahead and like and subscribe. If you have a problem that you'd like to see worked out, go ahead and submit that, and we can make that the next video. See you later, and think thrice.